Okay, good. Okay, so last Thursday was really the first real lecture on dynamical systems. We talked about sort of the basic ideas. So again, remember, the idea is that we have these nonlinear systems, a very large fraction of them, we are forced to give up the notion of closed-form solutions because they generate very complicated orbit sets that aren't well approximated. Now, there are many cases where we do have questions that require us to know quantitative solutions, and then you have to work very hard with these systems to do that. But in the general case, in particular, when we start talking about these chaotic systems, there's no way to write down closed-form solutions. So we needed a different set of ideas. And again, these all go back to the French mathematician Poincaré, basically more than 100 years ago, where we think about sort of the topological and geometric structures in the state space. So where are fixed points? Where are these limit cycles, and so on? So we have this notion of invariant set. There's this generalized notion of stability. We have stable invariant sets. Right? Invariant sets get mapped into themselves under the dynamic. Some of those are stable. If you're on it, you kick yourself, the vector field drives you back. Some will be unstable, you kick yourself and you go away, and so on. So we're really trying to build up, and I'll show that today in a very high-level way, kind of a classification system. So one of the questions we have here is, in terms of these basic objects that we introduced last Thursday, what kinds of behaviors can we expect in dynamical systems? So what I want to do today is give you, it's almost a contrast with the level of abstraction last Thursday. Invariant sets, attracting invariant sets, unstable, repelling invariant sets, and so on. The attractor base and portion separatrices. In some sense, that's very abstract. What I want to do today is step through, increasing in dimension of state space, 1, 2, 3-dimensional state spaces, and give you some concrete equations so we can hang our intuitions on some concrete cases. Along the way, illustrating different kinds of invariant sets and different kinds of behaviors. The end product of this is actually going to be a classification scheme in terms of what behaviors are possible as you increase the dimension of the dynamical system state space. And that's a key theme in qualitative dynamics, building up classification systems. Okay, so that's sort of the game plan. So we're going to start in one dimension. So this should look familiar from how we ended up at the end of Thursday. We talked about kind of a graphical analysis of a one-dimensional differential equation. So we had a state. In this case, we'll assume it's the real line. We have our differential equation. dx dt is some function of x. Right? The rate of change of x is some function of where it is in the state space. And we're interested in these invariant sets, in this case, fixed points. And that's where, basically, the rate of change of x stops, where x dot is equal to 0, or, as I just kind of illustrated with the SAGE homework, this criteria of x not changing turns into an algebraic equation or some equation to solve. So rather than think about where x dot is 0, that's where f of x is equal to 0. So we want to find those x's, x star, where the right-hand side is 0. And that will be where x dot 0, and all those points will be fixed points. Okay, good. Okay, so now we're interested in stability. So we've now imagined we solved that f of x is equal to 0, just like we did in the homework, as you will do in the homework. We have one or several of these x stars that are fixed points where x dot is 0. And I want to know if I perturb that state, if it restores itself and is stable, would be an attracting fixed point, or whether it's unstable. If I perturb it a little bit, that small perturbation will grow. So this is a basic question in calculus, right? So what we're going to do is, right around the fixed point, some particular state x, we're going to look at how perturbations evolve. Right? So I'm here, and I'm going to look at what happens when I perturb it a little delta x to some new state x prime. And how do we answer that? Well, kind of just to step up this slowly, well, what I can do, of course, is take this and plug this into the previous differential equation, right? I can say Now I put in x prime in here, and I have this small perturbation delta x. So what I do is just expand this all out, throwing away higher order terms in delta x squared, and just keeping the local or linear terms. The net result is we have kind of like a two-level system, if you will. I have the original dynamical system behaving, and then there's another coupled system, which we call the local linear system, which describes what the time evolution of this perturbation is, what this little delta x is doing. So if you just literally substitute this into that differential equation, expand it out, and then you factor out the x dot equation, the original equation, and then you end up with another differential equation that tells you the time rate of change of delta x. It's how these little perturbations evolve. And since we throw the higher order terms away, this is a linear equation. Right? So we just have here, it's the first term in your Taylor series, it's just this derivative of f. That's just the slope. So what it's saying is that we have the delta x dots evolve according to how big they are and just in the magnitude given by the slope. Okay? So we can just think of this as a number. The slope is just a number, lambda, and we have this very simple linear differential equation, which of course you can immediately write down the solution to that. Right? Things will either grow or die exponentially fast. The little perturbations x will either grow or die exponentially fast according to the sign of lambda, according to the sign of the slope. Right? So I already said this Thursday when we did that graphical analysis of that cubic one-dimensional differential equation. I kind of pointed out that the slope was important. So let's just get back to that. So now we have this classification. So this was the example on Thursday, this cubic, and I argued that so when the slope was negative, that meant that that was a stable attracting fixed point. Small perturbations came back. Well, we just did the solution to that. Those perturbations are dying exponentially fast because that lambda is negative. That lambda is so slow. So what I said kind of qualitatively Thursday is now completely analyzed here. So we have a classification scheme. We have a stable fixed point when the slope at the point is negative, unstable if it's positive, and then there's this neutral case. And lambda is equal to 0. And then you have to do typically a higher order analysis than this local linear system. Okay, so I'm kind of just recapitulating what we did graphically at the end of Thursday's lecture, and now I want to jump up to higher dimensions. But basically, the first point in this larger effort of developing a classification scheme, this is it. The only kinds of behavior you can get in one dimension are stable and unstable fixed points, or maybe neutrally stable fixed points. End of story. Nothing more interesting. Okay. So now, let's go up to two-dimensional flows and talk about what kinds of fixed points we can get in 2 dimensions. Again, so the form of the argument is directly analogous, right? So now, though, we have a point in the plane, we have a vector differential equation, or if we want, I can think of the 2 components of x as x vector as x and y, and the 2 functional components of f vector is little f and little g. So I can either write it in this vector form or think of it this way, little x dot, little y dot, and then there's a right-hand side determined by some function f of x and y that determines how x changes, and same thing. Little g, some function of x current state in the plane, tells me how y dot should change. And the concept of the invariant set or fixed point is the same, right? It's points in the plane now, x star, y star, such that the rate of change of the x vector is 0. Or we now have 2 simultaneous equations to solve. So this, suddenly, right? F and g I haven't specified. These could be complicated things. Actually solving this analytically is kind of complicated to find these. Small industries which do this. Thank goodness for our symbolic manipulators and numerical approximators. In the typical case, hard to do. But anyway, that's in principle what you want to do. You want to solve these 2 simultaneous equations to find X star, Y star, possibly a whole set of them. Okay, so that's reducing the question of fixed points in two-dimensional flows to quadrature, if you will. Go solve that somehow by hook or by crook. And now we have the question of stability. Again, we want to know, are these points in the plane, these fixed points, stable? Same thing, exactly the same move. We're at some point in the plane, and now we have a little vector perturbation in some direction, delta x. I plug that back into the 2D differential equation of the set of two first-order differential equations. Do my algebra, expand to lowest order, drop everything in magnitude of delta x squared, and I end up with the original differential equation and the local linear system. Again, so this is only valid around some particular state in the plane. But now now we're in two dimensions. What we have here, this is actually a matrix of partial derivatives. Right? I have partial little f, partial g, and then each one of those partial little x, partial y. Okay. So you have this sort of picture that we have the original system behaving, and then at each state, kind of a snapshot, some small little region around that, we approximate the vector field with just a linear set of equations. And then we're going to use that to, like we did before with the slope analysis, to determine the stability of the fixed point in 2D. And that's all going to turn on this object here. Okay, so now what I essentially argued for is the differential equation locally about a point is essentially just a linear differential equation. I just have the rate of change of the perturbation away from the fixed point that's given by some matrix. Right? And this matrix is called the Jacobian. It's this matrix of partial derivatives, partial f, partial f, partial y, partial g, partial x, partial g, partial y. Evaluated at the point I'm currently at, that the system is currently at. So I get numbers here, so it's just a matrix. So again, it's a local linear flow we're approximating. And in fact, given any type of linear differential equation that's in any dimension, well, here's two, you can write down a formal solution that looks very much like what we did in one dimension. Right? We had e to the lambda there. Well, that lambda was just a number. It was the slope of f. Here we have e to the matrix. So it looks like a formal solution, but maybe some of you have studied this before. We can talk about exponentials of matrices quite easily. And what we're going to do is do an eigenanalysis of this Jacobian matrix in terms of eigenvalues and eigenvectors to characterize this linear flow near this state. Okay. So just generally, so I've just reduced the problem of the stability of fixed points in two dimensions down to a linear differential equation. So it's a little bit of an aside. How do you solve linear differential equations in more than one dimension? You have some initial condition. We have x dot is some matrix times x. And what we're going to do is just analyze this matrix here, previously the Jacobian of the original flow, but just a linear matrix here in terms of its eigenvalues and eigenvectors. Eigenvalues lambda, eigenvectors v. I messed up here. There should be a v over here. To find the eigenvalues and eigenvectors, right? What we're looking for, the eigenvalues are directions that maintain themselves. Imagine v vector over here that are only stretched. They're directions that are only expanded or contracted at rates given by their corresponding eigenvalue. So a little bit of a review here, and you can write down the sort of formal solution of this way. In terms of the eigenvectors that you've gotten from matrix A, and then these expanding or contracting rates, these lambda, the eigenvalues of the matrix. Yeah, so just a little bit of a review, hopefully familiar. Sage provides a nice linear algebra package. Python provides a nice linear algebra package, so you can play around with some of these ideas. Okay, so that's, if we want to have a nice analytical form, we can analyze fixed points. In fact, it really didn't matter that we were in two dimensions. What I was saying, what I just said sort of holds in any number of dimensions. But as you can tell, moving back into two dimensions, the stability of the fixed points it's going to be governed by the Jacobian's eigenvalues, but just like before with the one-dimensional case. Okay? So just kind of a visual summary of this here. When the real part of these eigenvalues are negative, around our fixed point, the flow looks like this, just directly contracting. When they're both positive, we have a fixed point that's unstable, and so locally around that invariant set, we have this expanding vector field, a repeller. And it turns out the marginal case is pretty important. So this is where we have some mixture, where there's one contracting direction, right? An eigenvalue whose real part is negative, and then in a complementary direction, along the other eigenvector, its real part is positive. Now, I drew these axes 90 degrees to each other. In the general case, the eigenvalues and eigenvectors can have any orientation. So this is a kind of a mixed stability. It's partly stable, right? Stable manifold, unstable manifold here. And then there's a very degenerate case where the real parts of the eigenvalues are 0, and that corresponds to that original example I gave of invariant sets, just this purely circular flow. Think of this as, like locally, it's like a little simple harmonic oscillator. It's exactly, these eigenvalues are complex, and we have these rotations, pure rotations. Okay, and all of this is just done in terms of looking at the two eigenvalues of the Jacobian, just their sign, and so on. So I guess we are solving some equations here, despite my earlier admonitions. But it's local, and because it's local, we can get away with doing this linear analysis and having it tell us how small perturbations are damped or are amplified in terms of. So we can summarize all of this, these different cases, in terms of, different choices here. One way is to look at the determinant of the Jacobian. And as you may recall from your linear algebra class, that's just the product of the eigenvalues. So here what I'm doing is I'm just trying to summarize those previous cases in terms of basically the signs of the eigenvalues. But I'm going to use the determinant and then the trace of the Jacobian. So when the determinant is negative, it means that one's positive and one's negative. And that's going to be this sort of split mixed stability case, the saddle case, where there's one unstable direction, one stable direction. Okay, and then when the determinant is positive, well, we need to capture all the cases, we look at the trace, which is just the sum of the eigenvalues. So the trace of the Jacobian is the sum of its eigenvalues. You can show that when the trace is negative, even if one of these is positive, the other is a lot more negative, then we're going to end up with a stable fixed point. The opposite case here, when they sum up to being positive, and then we have this sort of marginal case we showed before with the cycle. So now I'm not going through in detail. This is what a real dynamical systems course would do. It would drag you through the proofs of the statements I just made. Not going to do that. We're staying at kind of a high level. Strogatz does go through this. But part of this is just to start to give us some sense of the kinds of qualitative descriptions that we can develop, classifications, without just thinking about general dynamical systems, in this case in 2 dimensions. So to kind of summarize this, you can make a plot of, now this is any sort of linear equation with some, a matrix or Jacobian, if you're analyzing a nonlinear system in its local stability. Look at the determinant and the trace. So now we think of these almost like the control parameters. We're sort of moving through different linear systems here as I vary A such that I get different determinants and traces. And what I just sort of alluded to before is when the determinant is negative, we have these saddles. So these are vector fields like this. That's a little hard to see through the camera, but this is the marginal case with a fixed point with one stable direction, one unstable direction. So everything over here, vector fields locally look like this. Okay. Then Up here, when the trace is positive, we have unstable, fixed point, everything's moving out. Sort of the opposite down here. Trace is negative, sort of the complementary case. The fixed point is now stable, everything is coming in. And then there's this interesting parabolic boundary, which is given by, and Strogatz works this out, you can see the details. It's this parabola here is a boundary between sort of pure instability and spirals, or pure stability and spirals. It's where the eigenvalues become complex, or where the complex component starts to dominate. So we have this marginal case here where the trace is 0. The two eigenvalues are equal and opposite. And we have the pure rotation. So over on this side here, right along this positive horizontal axis. Down here, negative trace, we have fixed point that's stable, but now we see some rotation in it because there's enough of the complex component of the eigenvalues is large enough to sort of overcome the direct contraction onto the point. And then just to finish up here we have fixed points that are unstable, trace is positive, but now there's a little bit of rotation as they move away from the origin. Right, so these are statements, kind of a set of lemmas or propositions, if you will, without solving any particular equation. It's true of sort of all linear differential equations. This is what they can do in terms of the fixed point stability. And yeah, so we're going to develop more classifications like this. Again, we're taking today kind of a higher level view of what's possible. So I'm just summarizing, which was probably several decades worth of mathematical work to get this all sort of cleaned up many, many decades ago. There's sort of other questions that come up that we're interested in two-dimensional flows. And that has to do with, if you recall from Thursday, we talked about the notion that a fixed point can have stable and unstable directions. I call them stable and unstable manifolds. And there was a lot of interest, mostly in the 60s, actually, curiously enough, developed at Berkeley around Steve Smale, mathematician down there, in the question, well, nature out there is very hard to model. A lot of it's often nonlinear. And how do I know that my model captures at least the qualitative features of the behavior in the real world? So this led to the notion of structural stability. Imagine if I write down some differential equation, I conclude, oh, I've got two fixed points and they're stable, and I have another fixed point that's a repeller and unstable. How much can I mess up my differential equation and still have that be true? How robust are my conclusions? Right? So one way to think about that is you write down your differential equation, and now on the right-hand side that specifies the vector field, I allow myself to do any possible little small perturbations. Take each vector and do this, and then, oh, do I still have a fixed point? Do I still have a fixed point? So that question was answered in some restricted cases in kind of a positive way. There's a notion of robustness of these conclusions you draw. We're talking about fixed points. What happens to the stability of a fixed point when I perturb the system, when I perturb the vector field? So that led to this analysis using these stable and unstable manifolds. So here's kind of a graphical description of a result along these lines in terms of structural stability. So here's our sort of starting point. So imagine our equation is such that we have a kind of split stability fixed point here. There's one stable direction, one unstable direction, stable and unstable manifolds like this. And the conclusion is that if the real part of these eigenvalues that specify the stability and instability along the two submanifolds, they're not 0, then for sort of all small functional perturbations of the differential equation, in other words, I'm kind of wiggling this stable and unstable manifold, slightly different vector fields, the fixed point doesn't change its stability type. Now, quantitatively, maybe the eigenvalues will change a little bit. Maybe it's a little softer or a little more unstable in this or that direction. But the qualitative conclusion that you have this mixed stability fixed point won't change. Now, the way we think about this geometrically is this condition that the real part of the eigenvalues is away from 0. In some sense, these two subspaces are kind of intersect in kind of perpendicular orthogonal ways, such that small perturbations just can't remove that intersection. So the actual proof of this requires some interesting topological argumentation. Now, you might say, well, okay, how could this go wrong? And this was actually where all the hard work was done. So this previous picture here, where the stable and unstable manifolds cross cleanly or orthogonally, it's called hyperbolic crossing. These are hyperbolic fixed points when I have mixed stability like this. There are cases, unfortunately all too common, where we have non-hyperbolic intersection. What I mean graphically is that the stable and unstable manifolds come in and they sort of touch. They sort of approach each other, asymptotic towards each other. So here's an example where I have a stable manifold and an unstable manifold. So I have a saddle fixed point here. But because the manifolds touch and are tangent to each other here, when I perturb this, some perturbations will actually break that tangency apart. And I'll end up with two fixed points. So this happens, for example, when the real parts, or can happen when the real parts of the eigenvalues are 0. If I perturb it a little bit, I'm going to make one of them a little bit stable, positive, a little bit unstable, negative. And that can change the qualitative conclusion. So when this happens, your analysis of fixed points, how many there are even, let alone stability, that can change. So we'll come back and show some other cases where non-hyperbolic or tangent intersections of stable, unstable manifolds give us grief or make life more interesting, lead to some interesting, complicated behavior. Okay. So this is just giving you a taste of how some of the sort of general results in dynamical systems are developed. Again, I'm not writing down some particular equation and showing that this happens. You can actually do this kind of analysis of functional perturbations of your equations and quite a bit of generality. Okay, so I mean, at this point you could say, well, this is sort of boring. These are all just analogs of equilibrium. I'm either going to a stable fixed point and sitting there. Well, that's kind of dull and predictable, or things are unstable. Can anything else happen in 2 dimensions? Right? Remember the conclusion before. In 1 dimension, you only had fixed points, stable and unstable fixed points. Maybe neutrally stable, but that's it. What else can happen in 2 dimensions? So now this is where the fun begins. So the other kind of behavior, again, I've already talked about this when I introduced examples of invariant sets. We can have stable oscillations. So these are called limit cycles. Now these are not points, they're one-dimensional subsets. They're isolated, closed trajectories that are periodic. And what do I mean by periodic? I mean that when I shift time by some number of seconds, called a period p, I come back. So in some sense, this specification of a periodic orbit it's almost like it's a fixed point, except it's fixed under integrating the equations for a period p. Right? State at time t is the same as that at time t plus p. So you can kind of pull out your sketch pad, and example of that would be just this circle, where after some period p, it comes back to itself. And so this is sort of a model for stable oscillation. And then in the case of a stable such periodic invariant set, we saw that before. We have states around the origin moving out to the limit cycle, and then states far away moving into it, such that if I'm on the cycle, I come in and kick my apparatus, the perturbations get restored, so I come back. So that's the notion of stability. Again, the flip side is that the limit cycle with the concentric invariant circles, that's not stable in a sense. you kick it, you go out, you add or subtract energy, and then you're on a different invariant set. So limit cycles are, in many ways, quite a different concept than behaviors you get out of a simple harmonic oscillator. You can flip the signs in your differential equation, or on the right-hand side of your differential equation, change the direction of the arrows to have an unstable cycle. So I'm just now stepping through the same sort of discussion we had before with fixed points, invariant set, but now if I perturb, I flow away, if I go to the outside, or I flow inwards to the origin. And, so those are kind of obvious, you can also have these saddle cycles. Right? So again, we have this circular periodic invariant set. If I perturb myself away, the vector field is pointing in, so perturbation's out, pushing back onto it. However, if I get pushed inside, I flow into the origin. So this is very much like the saddle fixed points we were talking about. Now, what kinds of differential equations can we write down that do this? Well, a really simple example of a stable limit cycle is you can do this in polar coordinates. So here's sort of the xy plane, but now imagine I'm instead describing the vector field in terms of the radial coordinate and the angular coordinate. So limit cycle is kind of simple, right? The angular coordinate just keeps increasing, constant rate. And then what I do is I stabilize it. I put in a fixed point for the radial flow, the radial part of the equation, in this case right around 1. And then if you do your analysis as if this was a one-dimensional differential equation, which we already did, you could show that the slope of this function was negative at r equal 1, therefore the radial component is stable. Well, that's kind of a cheat, but it captures the idea, but it's kind of a cheat. So here's another example, famous one, which I mentioned already, due to this Dutch radio engineer Balthazar van der Pol in the 1920s, and he was looking at this second-order differential equation. Now, if we just dropped this middle term here, x double dot plus x is equal to 0, that's the simple harmonic oscillator. So what he's doing here, turns out that the coefficient, when I express this system in the second order differential equation, the coefficient of the first derivative is a type of friction or dissipation. Maybe you've studied the simple harmonic oscillator with frictions. But what he did here is he modified this so that the dissipation would change sign depending upon the state. And the net result is sort of like the cartoon picture of the previous vector field. So now, curiously, the limit cycle is this funny, semi-dog bone shape here. And if you start outside, it very quickly comes down and then starts oscillating around. Or if you start in the interior, it'll cycle back out. So again, he was studying this with these tube oscillators. A lot of this was initially motivated by studying heart arrhythmias and also trying to understand ways of building electronic circuits that provided stable oscillations, robust perturbations that he could use for early radio technology for carrier waves. So now an important sort of methodological point here is very often the typical habit is we actually don't tend to write our differential equation in terms of various high-order derivatives. What we tend to prefer to do is to re-express them in terms of a set of first-order differential equations. So there's sort of a rule here. If I have an nth-order differential equation, I can turn that into n first-order equations. Well, how do I do that? Well, if I'm starting here, what I do is I just define a new variable to be one of the derivatives. So that then when I write down y dot, what's y dot? Well, y is x dot, so y dot is x double dot. So then I just kind of write out the right-hand side this way from the original equation. Just one way of keeping track of dimensions. Makes it easier, for example, how I can look for the two functions if I want to find the fixed points, the little functions f and g. What equations am I solving? And then where do I get the Jacobian? So it's easier in this form when we do that kind of analysis of fixed points and their stability and also the limit cycles. It's probably a little less intuitive, depending upon how familiar one is with second-order equations. And, in this form, it's a little hard to read off that this is the dissipation term, the kind of damping or non-damping term. But we will play around with this in the homeworks. So there's sort of a question. If I were to give you a pair of first-order differential equations that were coupled, or a second-order equation, well, presumably you understand how you'd go find the fixed points. Right? It might be hard algebraically to put the left-hand side to 0 and solve the equation, but kind of in principle you could kind of hunt around and find them. But how are we going to find limit cycles? Right? These are functions that come back to themselves after the period. You don't even know, when I first give you the equation, what the period is. So this is already a hard problem. That's why Van Poel's early work was so pioneering. It's actually completely non-trivial. It wasn't really treated mathematically until the 40s, during the Second World War, when people really had to get radar working. And so a number of British mathematicians started to develop the kind of first stages of limit cycle analysis. So the way this tends to work, kind of practically, is if you have a set of equations in front of you, and you want to know what kind of behaviors you've got, well, this is before you throw it on the computer. Right? Probably now we just throw it on the computer with our favorite integrator. We will do this, but kind of in principle, play along with me here. What you do is you show first that it can't have a limit cycle. So we know there are certain classes of two-dimensional systems, like I said, the simple harmonic oscillator. It can be rewritten as that. You're kind of done. There are oscillations, but they're not stable. Also, gradient systems. Whenever you can write down the vector field as the gradient of some potential, there are theorems that say that all you have are fixed points. No oscillations. And there's a generalization of this. Actually, engineers are quite interested in oscillations. In fact, suppressing oscillations typically in engineering systems, like not having bridges fall apart in the wind. So there's a generalization of notion of a gradient vector field, a vector field that comes from a potential. It's called Lyapunov systems. So these things, they only have fixed points. And depending upon your application, that could be a wonderful thing if you could show that. If you're, the system you're looking at, if you can show it's a Lyapunov system, or you can rewrite the right-hand side in terms of potential, you're kind of done. There's no limit cycle.
Those are classically conservative.
Yes, right. Well, okay. Okay, so we say classical physics. Here we go again. That's a special case in this, where we have position momenta, kind of conjugate coordinates, and they're it's true you can get these oscillations. So the simple harmonic oscillator would be one, but then those cycles don't have this kind of stability.
Right. That's the idea of conservative system.
Yes,
you
right.
Can't decay or
Right. So if you perturb it, that's tantamount to
stays in the system.
you've either added or subtracted energy, and that's it. It's constant from then on, and you've changed it. So you're on a different solution set. Right. So in the general case, we're looking at these kind of what you might think of as dissipative systems, that they don't conserve energy. A special case would be exactly where they do. So, yeah. Okay, but these are negative results here. What about a positive result? Well, here's the sort of general positive result. Again, you've got some set of two first-order differential equations, and can I show that it's got a limit cycle? Well, okay, maybe by this point you really have thrown it onto your computer, and you've integrated it, and lo and behold, it's like the Van Poel. It's got some little thing. You start with different initial conditions, you kind of explore around, and I'll be darned if there isn't a limit cycle there. Well, okay, but is it actually there? Is this numerical artifact? What? So it would be nice to have some kind of proof that this limit cycle exists. So what we appeal to is, it's called the Poincare-Bendixson theorem. And it's kind of typical of a lot of, or a number of topological proofs of non-trivial behavior. So the way we're going to think about this is, what we do is we try to invent some so-called trapping region. That's R, that's the pink-orange here, that contains this limit cycle, kind of guess. So you could imagine, you were looking at your Van der Pol simulation, you saw that dog bone shape. Well, who knows what weird nonlinear function of x and y the dog bone shape is, but you might try to pick a large circle. I can write down a circle, that's easy. That defines a solid disk that contains a limit cycle. And then also you want to find an inner boundary, maybe a small little patch around the origin, also a circle. And then what you can show, you try to choose these two boundaries such that this annular trapping region is such that the flow on the outer boundary always goes in. It can't go out, it always goes in. So from a distance, this is like an attractor. And then the inner boundary, the flow always goes out. Then the second thing is, now that you've characterized this region and it's like the Roach Motel, they go in but they don't come out, show that in this annular region there are no fixed points. Okay, we know how to find fixed points. Well, presumably you can turn that into showing that they don't exist in this region. If you establish those two things, then the theorem tells you you have a limit cycle inside. At least one. So again, it's a little kind of indirect, kind of nice. I mean, it's, I'd say almost elegant. Again, we're not having to write down the actual equations. And people do try to do that. People try to analyze that Van der Pol oscillator, that little dog bone shape. And boy, is it difficult. Those papers are hard-going analysis to actually get some decent approximation to that dog bone shape. But here, you can at least prove, kind of, give some support to what you're seeing numerically. In 2D, that's it. We have fixed points, and now we have this kind of new oscillatory behavior limit cycles. That's all you get in 2 dimensions. 1D, fixed points only. 2D, well, fixed points. Well, that's kind of obvious because there are 1D subspaces in 2D, so we should have fixed points. But the new thing is limit cycles, stable oscillations. So what about 3D? What can happen in 3D? Again, we can just import the lower dimensional phenomena. So we have fixed points, we have limit cycles. Anything new? There are 2 new things. So the first one is sort of a generalization of limit cycles. It's called quasi-periodicity. Okay, so now a little bit what I'm asking you to do as I do this simple overview is now you have to start thinking about vector fields in 3 dimensions. This is harder to do. Although we do have these nice 3D graphics processing chips on our laptops, so we can do some of this. Of course, it kind of begs the question, what happens if I'm in 4 or 5D? But we'll get there. Okay, so where we're going to think about this quasi-periodicity, it's the product of 2 limit cycles, such that their individual frequencies, the natural periods of each cycle, are not rationally related. That's what I mean by the interval, not rationally related. If they were rationally related, then I would do 2 cycles here and 3 cycles here, then exactly come back. And that would be topologically the same thing as a limit cycle. So what we're doing here when we're talking about these limit cycles having irrational frequencies is that they never quite match up, and they actually fill out a donut shape, a torus, constantly winding around. Again, if the 2 frequencies are rationally related, then they will eventually meet up, and that's essentially just a loop. Even if it's very twisted, it's still topologically just a loop. So to get a torus, in other words, what you should be visualizing here is the behavior is fills out completely the surface of this torus. Also, you should be imagining, if this was a torus attractor, that way out here, the vector field's all pointing in. I didn't draw that. And then inside the donut, it would be pointing out, such that if I perturb myself off the surface of the torus, either way, it gets restored. Okay. So mostly you're probably using your intuition from the lower dimensions when I said those things, but that's the idea. So you can have these solution sets. We have an invariant set that is, in the case the frequencies are irrationally related, that fills out a whole donut. That set is invariant. And the vector field's done right, it's stable. You know, if you were to look at this on your oscilloscope, you'd see sort of two basic frequencies, omega 1, omega 2. Do your Fourier analysis, which is perfect for this case, you'd see two spikes in your power spectrum. All the energy being concentrated at these two different frequencies. Okay. I said there were two things. Finally, the third thing is chaos. You can't have this in lower dimension for continuous time. Differential equations. So what is this chaos stuff? And I'll try to present it in a number of different directions, and we're going to pretty much focus on this for the rest of the course in a way, trying to understand how complicated these things are. So in a way, my introduction to this is going to be a little kind of fall short because there are a number of different properties we have to learn about to kind of circumscribe what this behavior is. So one way to describe it is that we're going to focus on stable behavior, but all I mean by that is that from far away in the state space, we get attracted to some region. But within this region, we have a very, very complicated invariant set, such that when we're on the set, it's almost periodic. We're sort of rattling around, and we pass by every state sort of arbitrarily closely on this invariant set. So it's recurrent, but it's also unstable. So how can we do this? So you kind of, again, so this is a little bit of an exercise in, unfortunately, 3 dimensions, but sort of 3-dimensional vector field imagination. I want something that is recurrent, so watch my hands, that's somehow in some set, invariant set, comes into itself, it's recurrent, but is also everywhere unstable. That kind of locally, if I do the linear analysis, like we were talking about before, I would always have some eigenvalue that showed that nearby perturbations were growing apart from each other. And it turns out exponentially fast. So this is like a set of design criteria for a vector field in 3D. So how can we do this? Well, it turns out there are any number of ways to do this, so I'll try one on you and we'll keep coming back, trying to make this more intuitive. So this is, when we move to 3D, this is really the new interesting behavior. This is what Poincaré discovered basically by hand in 1892 when he got his Swedish King Prize for solving, or actually not solving, the 3-body problem. It's kind of amazing how he could sort of figure this out. Okay, so here's one construction. There are many. Some of these are more intuitive than others. So this is going to be sort of a topological construction in terms of some of the objects that we've talked about already, in terms of stable and unstable manifolds and fixed points and mixed stability. Okay. So what I'm going to do here is I'm going to put, so now, again, you have to imagine, this is 3 dimensions. I have x, y, and z coordinates. I'm going to put a saddle fixed point at the origin, okay, and it's going to have a 1-dimensional unstable manifold and a 2-dimensional stable manifold. So z is going to be attracted to it, and like I said, x is going to be attracted to it. It's like unstable and y. So why am I doing this? Well, the first thing was I needed somehow to have this instability. So what I'm trying to do here is design a vector field such that if I'm flowing down along the positive axis and I get closer to this fixed point, nearby trajectories, nearby states get separated by that unstable manifold. Right? So you should kind of imagine the vector field's coming out and it's tearing it apart like this. So that's going to give me some instability. But now I have to make it recurrent. So what I do is I put two marginally stable fixed points out here that have a strong rotational component, and they're a little bit attracted, so that when, after I get pushed away along the unstable manifold, get pushed away from the origin, I'm now being pulled by this fixed point or by this fixed point. They're not stable, otherwise I just go into them. So they're unstable, but they have a large rotational component. And that rotational component will re-inject the solutions back along the z-axis. So I have recurrence, and then along the z-axis there's all this stretching, and that provides this. So this is the kind of an architecture in terms of fixed points and stable unstable manifolds. That was a question. I mean, maybe, at this point what I've done is argue that there should be such a vector field, and that's either convincing or unconvincing abstractly. In my mind, I can imagine such a vector field, but I've been doing this too long. So it turns out that there actually is a set of 3 first-order differential equations that have that architecture and support this recurrent instability. So these are the Lorenz equations. So Ed Lorenz just passed away 5 or 6 years ago. He was a meteorologist who was very interested in trying to explain. This is kind of a burning question if you're a meteorologist. Why is the weather unpredictable? So he was first studying these fluid flow equations, so-called Navier-Stokes partial differential equations, and there were various constrained geometries where you can have simpler descriptions of a flow. And in fact, there's a fellow named Salzburg who actually derived these equations that describe a constrained flow where you have fluid constrained between 2 layers, and the fluid layer is heated from below. And it was known that when the temperature difference is large enough, the fluid changes its behavior. So if the temperature difference is small enough, then the heat just diffuses across, and there's no bodily motion of the fluid itself. And then you reach a particular temperature difference, and buoyancy comes into effect. And so the water elements heated at the bottom layer become lighter, and they actually float up. They cool at the top, and they come down. And so what you get are these convective rolls. So that's the geometry that these now kind of abstract variables describe. What they do is they describe, it's a little indirect, but this is the basic intuition, how these rolls turn clockwise, or they're kind of paired, right? And then turn counterclockwise back and forth. And that the different directions are going to correspond to those 2 circular fixed points. So a little hard to see from here, actually. It's not obvious. In fact, Lorenz, when he was first studying this, it's nice to go back and read his paper in 1963 because, well, he didn't have computer graphics. I guess he didn't think to listen to it like Vanderbilt had done decades before him. What he had were, of course, printouts of x, y, and z as a function of time, and he was numerically integrating the equations. And he noticed that starting from different initial x, y, z values, it didn't blow off to infinity, and it didn't settle down to anything, but it also never repeated. So this is kind of a puzzle. I mean, he told me he spent months thinking he had some problem with his numerical integration package. Not the equations, there was a problem in his algorithms. So eventually he convinced himself that this was a real thing. Hence, this could be, this non-repeatability, he called it aperiodicity, could be just built in to the fluid flow equations that describe the weather, and hence an explanation for why the weather is unpredictable. So, if I just give you these equations, okay, first thing you do, where are the fixed points? Right? Okay, you have to do this. So we set this side equal to 0 and solve for the x star, y star, z star. You kind of get this out of your system. Find out where they are. You can immediately see the origin is 1, right? So some of this is easy. If I put in zeros over here, I get zeros over here, because x, y, and z always show up in each term. There's a symmetry. If I take x and y and I move it to minus x minus y, I get the same equations back. So the vector field has this symmetry about the z-axis, 180 degree rotation about the z-axis. I mean, presented with this equation, you kind of scratch your head. What can I figure out about these things? Another thing you can do is ask, how stable is it? And so there's a way, and Lorenz did this, kind of very nice kind of discussion in this paper. So I have this vector field, and I can think of it sort of like a flow, or if you remember your vector calculus or your E&M class, if I have a vector field, I can calculate the divergence of that to see how unstable or how stable the thing is locally. So this is a three-dimensional divergence, right? This is just the partial derivatives of this vector field here. And then integrate it over this region. So now, so he had in his mind a little bit, he had discovered by hand through the simulations that there was a trapping a sphere, kind of like that in the Poincare-Bendixson theorem. He knew there was a sphere of sufficient diameter that the vector field everywhere went in. So there's something going on in the origin. So you could say, well, what's happening to this sphere? Think of it like a solid piece of dough. Is it being sucked into itself? So that's what we can calculate. If we integrate this divergence of the flow over this whole region, well, it turns out in this case, we definitely lucked out, that this divergence is extremely easy to calculate. In fact, it's just, if I linearize the equations, right, the right-hand side of the Lorenz equations, it's just these constants, minus sigma, minus 1, minus b. This is about 10, this is about 8/3. So this is about 12. So what? Well, the rate of change of the volume is given by this integrated divergence. So we end up with this differential equation down here. It's a linear differential equation. And so we conclude that the volume, right, measuring the volume here, that it contracts exponentially fast. E to the minus 12t. That's fast. Right? It's kind of easy to see here why he just kind of lucked out with these equations. In fact, what you're doing when you take partial f, partial x, add on partial f, partial y, and partial z, you're really just looking at each equation in turn, and you look at the linear term in the corresponding coordinates. So x dot, I look at x, well, that's minus sigma. Here, I have minus 1 in front of y, and I have minus b in front of z. So in some sense, he just lucked out. This set of equations happen to be kind of linear in each of the three variables, and that's why this was constant. And he could immediately conclude, yes, well, it made sense. He saw this in the simulations. This volume was attracting extremely fast. So this all sort of circumnavigating. We're trying to figure out from the equations what properties we've got. We got something going on at the origin. So enough of that. Jumping, into the rapidly into the 1970s, one could then plot this out. So here's one solution to those equations. Like, where does it start? I forget. So what I'm plotting here, so again, x, y, the z-axis, and then the yellow trajectory here is started from some initial condition, and what you see, we'll do this on Thursday. I'll do a live demo at the beginning of Thursday lecture of this, so you can see it. But basically, you get this complicated solution set, and individual trajectory, and then this is one solution, kind of goes around, plots back over, and goes around like that. It actually has a certain geometry to it, which we'll talk about some more. But it's not some tangle of yarn. It has flat sheets out here. Something complicated has happened here, so you can't see in this projection how these two sheets out here come together, how they're sutured together. We'll look at that in 3D on Thursday. It satisfies these two properties. We have this sort of stretching apart due to the unstable manifold of the origin. That part of the vector is pulling these things apart, and they get re-injected constantly. The orbit never repeats. If it did repeat, then sort of the continuity and uniqueness of differential equations would say, well, that's going to repeat forever. It would be periodic. So This just keeps going and going and going like that. People have tried to understand the architecture of this set. So one idea is an approximation of these sheets here in terms of what's called a branch manifold. This is my terrible artist conception of this. But even still, it's sort of hard to find what the structure of this is. So we'll use a little bit of numerical simulation on Thursday to develop some intuition about this. Now, the other clever thing he did is, again, he didn't have access to 3D plotting back then. This is early 60s. He was running on an early IBM tube-based computer. But he noticed that when he plotted out x as a function of time and y as a function of time, z as a function of time, it was kind of oscillatory because of those circular fixed points. So he came up with this clever idea of plotting. He wanted to reduce the dimension from three-dimension flow. So what he did is he looked at the z of t time series and then just looked at the maximum of z of t over time. And then, okay, so here, that's what I'm showing you here. We have the green is some solution. And then I'm just putting a dot down when the maximum in z is detected. Z, 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 over here, z, z max, over here, z. So the clever thing was he could plot this. The next max in z versus the previous one. Right? Now, so he's trying to understand why is this, how can I explain to people that this is irregular, aperiodic? Right? So one thought would be, oh, the z maxima are like noisy. They're not predictable. And therefore there should be a scatter plot, and that would be a good way of demonstrating that this thing is hard to predict. In fact, what you get is this plot. So we have this cusp-like function, which is the next z maximum value versus the previous one. So the interesting thing here is it's not a scatter. If I'm at a particular z, there's a particular next z maximum I'm going to get. If I have a particular z value and I want to know what the previous one was, well, it's actually ambiguous. There could be two values that lead to that. But still, going forward in time, it's a function. Right? So we call this the z maximum return map, or returns. And you should think about, at least the use of the word return is just this notion of recurrence here. Come back up to the z. A priori, there was no reason this plot should be simple. I mean, if I just give you one of these complicated sets of 3 first-order differential equations, this kind of thing doesn't have to work. So he got really lucky. But anyway, then he could say, oh, this return map sort of captures all of the aperiodic behavior. In fact, there's sort of a nice analysis of this, which we'll get into in some detail. But he notes that this function here, so now we have a discrete time dynamical system, right? These now are maximum z values are discrete events. In fact, let me just point out that you can also look at the time of return. So this is z max value and how long it takes to come back to another z max value. That's pretty well behaved. And you can actually plot the inter z max time against each other, and it looks like a similar type of map. But it's basically the previous z max return map involved with this time of return function to get this. So there's nothing new going on here, really. This is just a simple monotonic function. So there's. But what he noted is if I'm down here and I sort of know the state of the system, which is a z max value, and I perturb that, and if the slope here is greater than 1, that small little perturbation gets amplified. So we'll go over this in some detail, but if the slope, well, actually the slope here actually diverges, but imagine there's some region here where the slope was 2. So if I start with z and I perturb it by some epsilon, that epsilon, it's going to end up with z values that are separated by 2 epsilon. There'll be a range. Well, then if I do that again, 2 epsilon turns into 4 epsilon and so on. So he argued there was this exponential amplification in errors along this sort of this chaotic component of the Lorenz attractor. And that was his, he turned that back into an explanation of why the weather's unpredictable. That it had built in that the fluid flow partial differential equations that describe the time evolution of this vector field, the flow field of fluid air and other things, had, even in simple constrained geometries, had this mechanism built in, that it could amplify these small fluctuations. So it was, now Poincaré had also suggested this in sort of mechanics, celestial mechanics, sometime before, and they didn't quite know about each other's work, but Lorenz's paper is particularly nice, nice analysis of this system and in the service of a real physical question. This construction of going from a three-dimensional flow to some lower dimensional, in this case, discrete dynamical system, we do this all the time because it's just easier to understand low-dimensional systems. So we're going to do this constantly. Might start with a continuous time differential equation and then map it over to some discrete time return map. Or we can just start studying return maps for their own sake. Right? If we're just interested in different kinds of chaotic behavior, Lorenz's construction shows that you can take chaos in the continuous time system, which only shows up in a three-dimensional state space, but then we can map this down to something where we can visualize a state space across the state space and study a discrete time system. So chaos can show up in discrete time systems in just one dimension. For three-dimensional flows, the sort of continuity of them requires you at least 3 dimensions, but we can reduce it down to a discrete time, lower dimensional system. So this now goes by the name of the cusp map. So here's a functional form of this. Right? This is easy to understand. In fact, in the early days, people just used to use their HP hand calculators to study these things. This is just, right, I'm plugging in a number between 0 and 1, the way I've normalized this. I get a new number, and I just do it again and again and again. This is a recurrence equation. I just keep doing it, and then the z value kind of hops around. And we can say, oh, can I measure the statistics of this behavior? What are the correlations and other things? How random is it? So we often study these simple low-dimensional systems, sort of for their own sake, to kind of capture different mechanisms. So let me finish with another example. These are the Rössler equations. Historically, and I'm presenting it in historical order, they came later, in the mid-70s, invented by this theoretical chemist, well, actually he's a medical doctor turned theoretical chemist, Otto Rössler. Interesting kind of fellow. Still alive. And he developed an interesting way of designing chaotic vector fields. So he has a series of papers where he calls this reinjection method. Basically, Otto was the only one who knew how to write down these equations. But he was a master at this. And so one set of equations was, so what he was trying to do, he wanted to come up with a system that he could sort of, in principle, design, build in this recurrent instability intentionally. Right? Lorenz stumbled across it because it came out of the fluid flow equations. He didn't design those, he was given those equations. Rössler wanted to design a vector field, so he had this notion of instability and then making it recurrent. His first attempts at writing out a set of equations, they were much more complicated, like dozens of terms, but eventually he figured out this set of 3 first-order equations. Now, the interesting thing about this set of equations, and this is kind of an important general point about nonlinear dynamical systems, there's only one nonlinearity in that whole system. You see it? In other words, if I take that out, I can solve this completely closed form. Put it in, I'll show you, all hell breaks loose. So that's sort of interesting. So you can't, so the lesson here is you can't look at your equation and say, oh, I've got more nonlinear terms. It's going to be more complicated behavior. It doesn't work that way. It really has to do with global properties of the whole vector field and how these properties relate to each other. It's not given in terms of a particular choice of symbolic representation. Just a single multiply can produce chaotic behavior. So there's not really a way to look at the form of the equations directly. Yeah?
Doesn't that also mean that even if you just try to throw out a small nonlinearity, you can't just throw away a small
Yes, exactly, right. You could radically change the behavior, right.
Even though you said these nonlinear effects
Right.
are small.
Right.
Doesn't.
Right, yes. Yeah, and so I don't know, maybe some of you have studied this area called perturbation theory, which exactly tries to do that. You do little perturbations, and you do little perturbations, and hopefully you kind of get your handle around it. And so for periodic behaviors, that's the way that the Van der Pol limit cycle was studied, using this. When the system is chaotic, it's exactly those little perturbations that blow up in your face and make it so you can't write down a closed form solution. So that's actually kind of the form of the proof that you can't write closed form solutions for these systems. Yeah.
This might not be answerable, but in line with what you said, if you put a parameter in front of the z, so that you kind of could minimize the z component.
Oh, yeah, yeah.
Would that still maintain chaoticness all the way down to zero size, or the limit? Parameter goes to zero.
Good project. I don't know. We will study the Rissler in terms of A, B, and C. In fact, first I'll show you. Next week we're going to talk about what's called bifurcation, how the behavior changes. So far we've been talking about what kinds of behavior can there be, and then a second question is, how do these behaviors change into one another as they vary some system parameter? So we'll look at that as a function of C. This is an interesting what this comes about. Let me just show you the attractor here and try to summarize things. So this is, again, one solution of the, starting from one initial condition, one solution trajectory for the Rissler attractor. And I'll show you this in 3D on interactive 3D on Thursday. But sort of this flat racetrack, and it kind of spreads out and folds over on itself. You can kind of, in fact, this is even worse. I have to do a better job of this. The branch manifold is just kind of a flat, two-dimensional rubber sheet that gets stretched out and folds onto itself. I will convince you of this more directly on Thursday. You can do something just like Lorenz. You can say, oh, if this is the x-axis, I'm going to look at x-max values and look at the return map, x-max return map. So again, reducing it down because I don't always want to look at the 3D system, and so this is what you get for the Rissler. You get this nice little hump map, next x-max versus previous one. And we have kind of abstracted that out now to something called a logistic map, and here's a functional form for that. It's just a quadratic function of this. The state space is just the unit interval. Map this quadratic function, maps this to itself. Right? So it's a function going forward, and then it's ambiguous. So if I want to know if I have the next value, there could be two previous values that lead to that. Okay, so just to kind of finish up quickly here. So what we did today was basically just do a tour of what kinds of behaviors we can get. I was trying to be, on the one hand, kind of argue for these general classification schemes, stability, instability of fixed points, so on. But then also as a function of dimension, right? So in one dimension, we just had fixed points, stable, unstable, saddle. 2 dimensions, we had fixed points and limit cycles. In 3 dimensions, fixed points, limit cycles. I briefly talked about the quasi-periodic torus attractor, and then the Lorenz and Rissler attractors, and talked a little bit about their geometry and how you could think to construct them. We'll come back and analyze this in detail. Chaotic behavior is really going to be the main focus. Now, the question is, what goes on in higher dimensions? Well, it's obvious. We can import all of this stuff in higher dimensions. But what are the new things there? And at this point, we sort of run out of ways of my waving my hands at you or showing you graphics, right? So what are we going to do? I mean, presumably it's plausible that there are really complicated behaviors in higher dimensional systems. You know, to a certain extent, the kind of geometric approach, even if it works in principle, is not very helpful. So we're going to need some more quantitative ways to talk about stability and instability. And the hint for this is to go back to that Jacobian and the eigenvalues that we were using to classify stability of fixed points, and we're going to turn those into sort of measures of average, sort of along a solution, stability and instability. So those will be the Lyapunov exponents. And then, one benefit of that is we're actually going to, that'll give us some hint of how to extend this classification system to any dimension. And that will be sort of the most general classification scheme that we have. So, I I gave you concrete equations, and we're going to be using these in the homeworks and so on, so you can start playing around with these things yourself. Find their fixed points, do stability analysis, and then start looking for the more interesting behavior there. So, and this is really the end of the kind of the big picture. By the big picture, I mean, I give you a dynamical system, and I want you to tell me how it behaves, right? So I said the kind of main goal is somehow figure out this attractor Bayesian portrait. Well, we just talked about a lot of interesting attractors. That's a kind of semi-local view, these invariant sets and their stability. It's kind of a semi-local view. Then you step back and figure out the whole state space. But then there is also the question of what happens when we have controls on these systems. How does one kind of behavior turn into another kind of behavior? So that'll be Thursday and next week. So we're still here in the class, right? We're still trying to figure out what can nonlinear nature do. So it's going to occupy us for another couple weeks. Okay, so that's it.